Good morning.
Good morning to all of you. Good morning. Hi,
Good
Jason.
morning.
We can try if you can share screen, but I'm afraid we have to wait for Marco. Jason, can you maybe try it if you can share your screen, please? I don't think you can.
I'm not able to.
No, right. Yeah, I was afraid for we have to wait for Marco, the big man of the Remtech. He has to allow you to open it.
Okay.
We wait a little. Morning, Antonella.
Good morning, Frank. Hello, everybody.
Good morning, Antonella.
Ciao, Jason.
Antonella.
Marco?
We're
He's not
waiting
here
for Marco.
yet.
No.
He is too busy.
Yes.
He has 2 sessions to open, so he jumps from the one session to the other.
Yeah.
He's extremely busy, Marco.
Yeah.
I wonder how he stays so calm, always calm.
No, he has this attitude of being always relaxed, calm in the public sessions. I know him since 2002, so
Okay.
almost 20 years.
That's a long time.
So
That really is a long time.
yes. We have been in the same room almost 10 years.
Then okay. Yeah. That's really the way.
Room.
Yeah. So you know all the ins and outs, eh?
Yeah.
Unfortunately, we don't have the time to share all the details, but next topic we do that. That would be a good thing about a live meeting in Ferrara. Eh? In the evening, we can share a little the nasty details.
Yes, I have the train at 3:30 p.m. and this evening I will be in Ferrara in person. So tomorrow I have a session not online. So I leave Rome in the afternoon.
I think you're also involved in some Italian sessions, eh?
Yeah.
Yeah. It's also in Italian language, eh?
Yeah.
Oh, yeah.
Yes, there is the international session, Remtech Europe, and the national sessions in Italian.
Yeah. And tomorrow is all national sessions, all day, or only the morning, or?
The Italian session is parallel to the European one. So there are many sessions in the morning and many sessions in the afternoon, overlapping. So many things in Remtech.
Yeah.
We are in Italy. We are very fascinated by contaminated land management.
Yeah. It could be that Italy is the European country that is most active in the field of contaminated land management.
Yeah,
you have so many workshops and initiatives.
Yes, and we have also in recent period also many changing in legislation because this new European funding for Next Generation EU and so on forced to also to push the ministry in changing the the legislation to simplify the procedure. I don't know if this new legislation will simplify the procedures, but they try to to do this.
Okay. But the goal of it is to simplify the procedures. That's why you do it.
Mainly the administrative procedure, because the regarding the technical part, my institute, the scientific community, also the agencies are very active, and we work together very well. But as in the southern countries of Europe, we have this administrative part that is not so in touch with the technical part. So from the technical point of view, we can solve the problems, but in many times the procedure stops because there is an administrative binding or obstacle. So this is why the ministry tried to simplify. But lawyer will write down the piece of law, and not technical people in many cases.
Yeah, I do not want to be cynical, but I heard the line making the procedure simpler a little bit too often. We had several stages in the Netherlands making the procedures easier, and it really didn't get easier. It got more complex, simple as that. So I'm a bit skeptical, to be honest.
Yes.
I think Marco arrived.
Hi guys,
Marco,
can you hear me? Can you hear me?
Oh, Marco!
Hi. Did you, Frank? You did already the trial with the presentations?
We tried, but they are not allowed to share the screens yet.
Oh,
so
okay,
you have
okay.
To,
just
you
a moment.
Yeah.
I will solve it in a minute. Just a moment. Okay, Mark, you can try to share your screen for the moment. Okay, put full screen mode. Okay, go down till the end.
Okay.
Okay, perfect. Stop sharing. Jason, your turn.
Yes.
Full screen, okay. Thank you, Jason.
Perfect.
It seems perfect. Go down till the end. Okay. Okay, stop sharing. Okay, and then who is missing? Laurie, please start your presentation and share screening. Okay, you have a Prezi.
Yep.
Presentation, so it's more risky than the others. Common PowerPoint. So please go down.
Yep. No
Looks
problem.
Okay. It seems.
No problem at all.
It seems working.
Yep. Okay.
Kuala Lumpur.
That's so nice.
Thank you.
Okay, I don't know who is missing for the trial. Marianne, please start sharing your screen. Perfect. Go down till the end.
Okay.
Also works fine.
Marco, should I go?
Okay, yes.
We have Tom Horton.
Tom is missing.
Oh, he's
Yes.
here.
Yeah, okay. Tom, do you want to make a trial of your presentation? Your presentation, just one, yes.
Going down through my screen to the end, you can see it.
No, not yet.
I wonder why. This is the same thing that happened yesterday.
You have to click the green button, share screen, and then choose the screen with your presentation in full screen mode.
Share screen. You see my screen?
No.
Same thing that happened yesterday.
Do you have a Macintosh probably? No, no.
No,
Just
no.
asking. It's a problem. It's a major problem, Tom. Frank, by the way, you have a plan B. You have your presentation from Tom from the shared folder.
I can check.
Because we can go with the next slide, please. Phrase. It's not the maximum for a professional presentation, but you know, it's a plan B.
I have all shared folders available, but not for session 18, unfortunately. So I have to look.
I will check. Tom is the third speaker, so it's really something that.
Yeah. I'll do that during I need some time. I need to go to the.
Okay, and we are going to open in 3 minutes.
Hey, Tom, you need to.
Asking Lori. I'm asking if Tom is near you in your hotel.
Yeah, well, he's across the street, so I could go across the street, but he's right before me, so I could go over there right now and try and get him started.
No, but maybe Tom could join you where you are with his USB pen. You have
Marco,
Tom,
Marco,
if you push share screen, then click your screen that you want. You have to click share screen again a second time, because then it says to basically turn it on. So you share screen, click your screen, and then the bottom right-hand corner, there's a blue button that says share. You have to click that after you pick your screen.
Oh, and then bottom, there's a green button for share screen.
Right, click the green button, click your screen, and then on that same where you're picking your window to share, on the bottom right is a blue share button. Push that. There you go.
You see my screen.
You are a magician, Lori. No, it was me that was not explaining well. No,
no, not at all.
No,
but yeah,
probably Tom is used with the Teams or other means. No.
Yes.
Okay, we can see it. Tom, please go down till the last slide.
Yeah.
Now, Tom, yeah, make sure you keep this up. Don't close it down. Just keep it as is. So when you go to share, it's already ready.
Yes.
Okay.
Don't close
very
the
good.
presentation. Yes, very good.
So
okay.
then should I click stop sharing? How do I stop sharing?
Click that stop sharing at the top, and then you're done. And just leave. You go back. You go back to the beginning of your presentation, Tom. So you're ready when it's your.
Are you right after me, Lori?
Yes.
You want to go one? You want to put one space?
Frank, an information for you, Antonella and Tom. Welcome, Tom. We have to stop exactly at 13:30.
Okay.
We have then the sustainathon, and we have to organize a number of things. So it's not a problem 5 minutes, but I cannot give you the 15 the usual 15 minutes. Just 5 minutes to address the last question or the last remarks, and then that's it. No, so not 15 minutes, but just 5 minutes after the.
It's no problem. We only have 6 speakers, so we have plenty of time for the discussion.
But you know that with the measurement on Aeriforms stimulate a lot of questions. There is Antonella online, and she has a lot of questions for any speakers. Sure. No, so it is a moment that you arrive at 2 p.m. No, so pay attention on this.
Yeah, no worries, Marco. We will fix that.
Perfectly. Okay. 11:30. Antonella, please.
No, don't worry. I will not take extra time for questions.
I know that you have a number of questions that not easy to respond. No, not a yes or no question. No. So, but it's important, however, the final panel, because people are expecting this. People is going to arrive. So we can wait
a little longer.
Yes, we can wait a couple of minutes. Maybe Frank, you may share our timetable if you have it at hand, or I may do it if you like.
I don't have that available, Marco. Sorry.
Okay, I will share my screen just a moment in a way that if we while waiting we are showing where we are in the program. Are you able to see it, Frank?
Yes, sure. Yes, we see the program.
Perfect. Okay, so guys, attendants, just a few minutes. We are waiting for people arriving. You know, there is ever a bottleneck in people joining the session. So I take these 2 minutes to explain where we are in the program. Now is starting in 2 minutes the session 18, Aeriforms and vapor intrusion measures and model. There will be 3 chairs, very expert on this field. Frank Spartis, Antonella Vecchio, my colleague, and that I work every day, and Thomas Fry from Scotland Contaminated Land Forum. On the other room, we will have the groundwater remediation in difficult conditions. So if you don't see me online, I'm switching between the 2 conferences. And then I would invite you all to join at least for 1 hour the Sustainathon, this marathon of 24 hours where 50 more speakers will go in deep with the 17 Sustainable Development Goals, how they have applied it in their country. And so at least I don't ask you to stay for 24 hours, but at least 1 hour, so that you have participated in this first edition of this challenging event. For otherwise, for who is more, let's say, targeted on remediation issues, there is also an alternative, state of the art of contaminated sites in Brazil, that is organized by AESAS, that's the Brazilian Association of the companies that works in the environmental field. No, so they will present how the state of the art on how they performing the remediation and how they are performing characterization with the resolution site characterization, a number of issues that you can follow by the complete program of the session. That's I try to occupy those 2 minutes. Frank, Antonella, and Tom, floor to you for the presentation of the session. Please introduce yourself. Frank first, then Antonella, and then Tom.
Thank you very much, Marco. Welcome, everybody. Good morning, good afternoon, good evening, wherever you are in the world. As Marco said, we're starting session 18, another session on vapor intrusion. We all know it's difficult to measure vapor intrusion. It's also difficult to calculate. And often what is difficult is also very interesting, at least from a scientific viewpoint. 3 chairs, I'm one of them indeed. Frank Swartjes, I'm working for 35 years now with a lot of enthusiasm on contaminated sites. I did it most of the time, that is 30 years, employed from the National Institute for Public Health and the Environment. Antonella, would you be so kind to introduce yourself?
Welcome everybody. Antonella Vecchio from Italy, National Institute of Environmental Protection and Research. Since 2003, I'm working in contaminated land management, and my main job is site-specific risk assessment, human health and environmental one. And in the last 10 years, I was involved in the development of national guidelines on vapor intrusion in contaminated sites.
Thanks a lot, Antonella. Tom, please, can you introduce yourself?
Yeah, good morning, everyone. My name is Tom Asprey. I'm technical manager for a UK-based remediation contractor called ERS. Today, I'm also representing the Scottish Contaminated Land Forum, which is a volunteer group of people in Scotland interested in contaminated land. This is not an area of expertise for me. My day job is very much around lab to full scale treatment of soil and groundwater. So I'm looking to learn today, really.
Thanks a lot, Tom. I give over to Antonella, who will lead us through the first part of the session. Antonella, please go ahead.
Okay, let me introduce the first speaker. Is Marianne Mombrun from Bordeaux IMP that will present an interesting monitoring technique for soil gas assessment and vapor intrusion. Marianne, please.
Yeah, thank you.
Thank you.
Everything is okay for everyone? You see my screen?
Yes.
Okay, I will start. I am Marianne Mombrun. I work in Bordeaux, like Antonella said. I will talk you about study of the flux organic pollutants, measuring actual surface gas fluxes of organic pollutants. When converting an industrial site, it is essential to take into account the risk associated with the presence of gases emanating from the soil. To do this, various factors must be taken in account, such as the history of the site and its future. At the beginning of our research, we tested two different measurement and sampling systems on an industrial site. Sampling stick, as you can see on this picture, I'm sorry. Here. On the little picture on the right, as you can see, with a retractile tip and pitch there. Simplistic, as you can see in this picture, the measurement points are very close to each other, around 20 centimeters. In green and purple, two fixed pieces, and blue and orange, the sample stick. On this slide, the results of the analysis of the following compound, TCE, TCE, PCE, obtained with the two sampling technique, fixed pieces in purple, in orange and blue, with the sampling stick. The result varied significantly from measurements that were very close to each other, around 20 centimeters, regardless of the technique used, as well as a restrictive implementation to reach depth between 0.2 meter and 1.5 meter. Use a lot of material like a jackhammer, hydraulic impact hammer, generous, pickaxe, and more. Difficulty in establishing concentration gradient due to the soil heterogeneity, that's why surface flux difficult to estimate. In addition to this difficulty, the integration of the water fluxes from the surface to the ground must be taken into account. The higher the concentration in the soil, the lower the gas flux to the surface. The addition of these parameters make risk assessment more complex. We were therefore interested in using a fluxes chamber to increase the surface of the measurement and obtain a more representative average flux than a single point sampling, like stick or piezo. The important point regarding surface flux measurement being the surface volume ratio and of the measuring tool. We're designing a flux chamber that you can see on the picture with a 5 centimeter side and a height of 3 centimeters, which represents a volume of 7.5 liters. On the explanatory drawing, which we see the measurement sequence composite of the flux chamber on the floor, the PID sensor, a gas recirculation pump, and CO2 sensor, with a spigot awaiting a sampling at any time in a Kevlar bag. We made two fluxes chamber, one to be inserted in the soil and a second to be pushed on the floor with a system of seal to ensure waterworthiness. On a limit in which we control the gas injection, we compared the results obtained by the two tools. The result be comparable for the each of implementation. We retain the flux chamber pushed on the floor. This is mobile flux. Our flux chamber pushed on the floor, mounted on its radio-controlled movement system. We can see the different parts to the tool, CO2 sensor, PID sensor, gas pump circulation, automatic frame, and the flux chamber. The implementation of mobile flux is based on the following methodology. Step 1, we prepare the planting area. Step 2, we install mobile flux. Step 3, we push on the floor the chamber flux. After 8 minutes, we can take a sample gas and we can pass at the other point. We're pulling up the chamber flux and we move all the mobile flux to do another point. As you can see on this video, we have tested mobile flux on a very rough terrain over a long period of time, around 7 hours or 8 hours. This does not pose any difficulty in movement. We have therefore applied this methodology to our tool on a real industrial side. The objective was to map the gas surface fluxes with a resolution higher than 5 existing pictures. We conducted this study on a 10,200 square meter site with 5 existing pictures, the blue circle in the picture. Previously, different compounds were detected, DCE, TCE, and PCE. This site presented dense vegetation, very dusty soil, and we work under high heat. Despite some difficulty, we mapped the area with 20 points with mobile flux over 6 hours of time, with confirmation of the result obtained of the measurement of the existing pressure. On site, with many stones large than 5 centimeters in diameter, the use of sunken flux chamber is impossible. Our would require a heavy preparation of the site before measurement. We are currently working on improving the sealing system with the aim of being able to carry out reliable measurement on uneven sites. Our tool, mobile flux, can reach good precision compared to classical inserted one. If we work in the good condition, can reach good precision compared to classic inserted one. We must remain very vigilant on the PID measurement and the sealing of the flow chamber on an heterogeneous surface. On the other hand, the mechanical part of the radio control have been tested and are operational. From our point, flux measurement, we would like to be able to obtain a representative estimate of the risk liking to VOC emission over a year. We are therefore currently working on a correlation between the measurement obtained with our system and the rainfall event influencing the flux rising to the surface. To have a better estimate risk. Thanks for your attention.
Thank you, Marianne. Very interesting presentation.
Thank you.
Okay, so let's move to the second speaker, Jason Virginelli, who will present a screening tool for the exclusion distance from vapor intrusion at petroleum contaminated sites. So, Jason, please.
Okay. Thank you, Antonella, for the introduction.
J'ai eu des questions sur le chat.
Okay, so the focus of my presentation will be on the vertical exclusion distance for petroleum vapor intrusion. That is a concept quite consolidated in the US and in Australia, while at least to my knowledge is something still not considered in Europe. Now, the starting point of this presentation is large evidence that we have from the literature regarding the natural attenuation of petroleum hydrocarbons in the subsurface. Indeed, it was largely demonstrated that petroleum hydrocarbons vapors can be attenuated by several orders of magnitude within very short distances. So based on this evidence, it was introduced this concept of the vertical exclusion distance. That is the source to building distance beyond which the potential for vapor intrusion can be excluded, as we can expect that petroleum hydrocarbons will be attenuated at a level that does not pose a risk for human health and in general for safety. So to identify this vertical exclusion distance, in these years were proposed different methods. Here I have reported some technical documents, some papers proposing different methods for the identification of this vertical exclusion distance. But more or less all these methods start from the analysis of soil gas data, typically using multi-level nested probes, such as in this example. And then from this soil gas data, it is possible to identify which is the thickness of clean soil needed to ensure an attenuation of petroleum vapors at a level that can be considered acceptable from a risk-based point of view. And this approach was the one largely applied in the US, and around 10 years ago, more or less, were issued a database by US EPA containing this vertical exclusion distance data estimated using soil gas measurements in more than 100 sites. And here I have reported an example of the results contained in this database. You can see here the vertical exclusion distance, the empirical vertical exclusion distance estimated as a function of the source concentration, considering as the target compound benzene, considering that, assuming that benzene is typically the risk driver for petroleum vapor intrusion. You can see here that the vertical exclusion distance is estimated on the field is typically in the order of few meters. Then the next step was to statistically analyze this data in order to set some general criteria. And here are the criteria proposed by US EPA for petroleum vapor intrusion. They propose a vertical exclusion distance in the case of a dissolved phase contamination of around 2 meters, while in the presence of El Naples, it was proposed a vertical exclusion distance of around 5 meters. So this means, in other words, that if our source of contamination is at a depth greater than 5 meters, according to this approach, we can exclude the vapor intrusion pathway for petroleum hydrocarbons. Now, these criteria were estimated from the empirical data, assuming a certain level of confidence. In particular, these empirical criteria were estimated assuming a level of confidence of 95%. This means, in other words, that these criteria proposed by US EPA can be applied in 95% of cases, but we can have some situation where these criteria cannot be applied. In order to identify which are these scenarios, we believe that mathematical modeling can be of help to identify which are the conditions for which this natural attenuation can be not so effective to attenuate petroleum vapors. And this is the aim of my presentation. So I will show you the results of some modeling work that we have carried out during these years. I will start with a one-dimensional analytical model that we have developed some years ago. This analytical model is based on the same assumption of the Johnson and Hittinger model that is the most widely used model in the risk analysis procedure. But here we have also included the aerobic biodegradation. Aerobic biodegradation limited by oxygen availability. And so we have included in this model also the oxygen transport and consumption to sustain the aerobic reaction. One of the key novelties of this model compared to other models available in the literature is related to the fact that in this model we have considered for the oxygen replenishment the presence of the building. And we considered the presence of this building as a surface capping to oxygen penetration. So as an impervious slab that can limit the oxygen penetration in the subsurface below the building. And to do this, to account for this effect, we have introduced an equivalent diffusing length for oxygen as depicted in this blue arrow. So in this way, we kept the simplicity of the one-dimensional model as the Johnson and Hittinger model, but we have considered this effect of the building footprint. And to validate this approach, what we have done is to compare the results of our analytical model with the results obtained using the same input parameters obtained with the numerical model of Abreu and Johnson. That is the numerical model used in all technical documents issued by US EPA on petroleum vapor intrusion. And you can see here on the right the correlation of the results obtained by our model and by the numerical model. You can see that we obtain a good correlation. And this correlation is mainly ascribed to the fact that we have introduced this equivalent diffusing length for oxygen. Indeed, here on the left, we have reported the results obtained again with our analytical model, but without considering this building footprint. So simply considering the oxygen replenishment that we can expect at open ground condition. You can see here that in this case, the correlation is quite poor. So highlighting that the approach that we propose for the diffusing length of oxygen is effective. Then once that we have highlighted the validity of our model, we then calculated the vertical exclusion distance as a function of the source concentration. And we have calculated this vertical exclusion distance assuming these different biodegradation rate constant, reported here with the different colors, by varying this biodegradation rate constant in the range expected from the literature for benzene. You can see here that the trend expected by the model is consistent with the field result. So we can say from this first comparison that the empirical data of US EPA are also supported by mathematical modeling. Of course, these results depend on the input parameters that we have selected. So in order to extend this evaluation, what we have done is to carry out a Monte Carlo analysis. The Monte Carlo analysis consists in running a large number of simulations. In this example are 1,000 simulations, randomly varying the input parameters within the range that we can expect in the field that I have reported here on the right. And then once that we have performed this simulation, we have analyzed the results in terms of the frequency of the calculated vertical exclusion distance by our model, and also in terms of cumulative frequency. You can see here from these results that in most of cases, the calculated vertical exclusion distance is lower than the empirical distance proposed by US EPA or by CRC CARE. Although we have found some cases for which the expected vertical exclusion distance should be higher than the, for instance, than the 5 meters proposed by US EPA. And so the next work was to identify which are the scenarios for which we can expect that these screening criteria proposed by EPA can be not enough conservative. So what we have done, first of all, is to investigate the role of building. The role of building in terms of dimension of the building. Indeed, if we consider the building as an impervious...
Sorry, yes, on 2 minutes you have.
I will, yes. If we consider the building as an impervious slab, then the larger the building, the lower the oxygen availability at the center. So we have developed this analytical model, and from this analytical model, then we have prepared some nomographs, such as the one that I have reported here, that allows to estimate which is the dimension of the building above which we can expect an oxygen shadow at the center of the building. That means an anaerobic condition. And here, for instance, considering a source concentration of 10 grams per cubic meters as a source concentration, the critical slab dimension is normalized to depth is around 4. That means that if we consider a source depth of 5 meters, the critical dimension of the building is of 20 meters. Another aspect that we have considering is the presence of methane in the source. So in this case, if we have a high source concentration of methane, then we can expect that the empirical criteria proposed by US EPA are not valid. And in particular, we have found that when we have a methane concentration higher than 8–10%, then the empirical criteria proposed by US EPA are not more valid. I will finish my presentation just showing another tool that we have developed some years ago, that is a two-dimensional analytical model that allows to simulate the profile of benzene and oxygen in the subsurface. We have validated these the analytical model with the numerical model of Abreu and Johnson. You can see here in this example that the results that we obtain are very similar to the ones obtained with the more sophisticated numerical model. And then we have implemented this analytical model in an Excel-based tool that is named PVI2D. This tool is available for free from this website. And I believe that this tool can be of help for supporting the application of the vertical exclusion distance criteria proposed by US EPA. So I finished my presentation here. I have reported my mail and some further readings with the models that I briefly presented in this presentation. So thank you for your attention.
Thank you, Jason. Very interesting presentation, also your presentation, very interesting modeling. And I will move to the next presenter. Thomas Hutton from the Clean Vapor, that will present another interesting presentation on how do we have a good monitoring plan for assessing vapor intrusion. So Thomas, please.
Yes, thank you very much. And today's topic may not be the most exciting topic that you're going to hear about, but it's probably one of the most important things that goes into a vapor intrusion mitigation system. And that is how the operation and maintenance and monitoring of that system proceeds after the system is installed. Ultimately, the purpose of a vapor intrusion mitigation system is to be protective of human health. We do a lot of science and a lot of design work into design and building these systems, but if they don't function as they should to be protective of people, the value is not all that great. So we need to keep always focused on whatever we do in our science is to be protective of people. Because the most important asset that we have in our planet and our community is people. And it's very important that the people who occupy these buildings after we put these systems in are protected for a long time into the future, and that we have a record of them being protected. The second most important thing, and this is probably applies more to the US than other places, is protecting the responsible parties from long-term liability. Their hedge funds, which are investment companies, have discovered that vapor intrusion is a good source of money. So what they do is they fund law companies and attorneys to troll for lawsuits that involve vapor intrusion, and then they go and sue the responsible parties. And in the US, we have had sites that have had awards as much as 20 million, and 14 million of that award was actually punitive to punish the responsible party for not dealing with things in a responsible manner. So a successful O&M plan, operation, maintenance, and monitoring, starts in the design phase. That's where you're figuring out the things that you want to monitor for, you want to measure, and what are the metrics of a successful mitigation system, and how will you measure those things and record them to assure the functionality way into the future. That starts with getting stakeholder buy-in. Stakeholders are usually the responsible party, the building owner, the attorneys, the people who are installing it, and the investors. And if you don't get this from the outset, it will be a troubled project. You also have to be honest about what the costs are going to be for operating and maintaining the system way into the future. So those costs can be set aside as reserves and escrows to make sure that there's at least 20 years of reserves to run these systems, because most of these systems are not going to scrub the soil clean in any quick amount of time. They're just designed to protect human health. They're not really extraction systems. So what are the performance metrics that you want to look for? Not typically what we look for in a vapor intrusion mitigation system is monitoring the vacuum that's applied, the total airflow out of the system, the sub-slab pressure differential, and power that is consumed. Power is one of the things we watch because it's a critical cost after the system's been installed. But it also, if you watch the power to vacuum and airflow ratios, it will be a good offsite indicator of how the motor is performing and maybe when the motor needs to be replaced. So the most important thing that you can monitor in a vapor intrusion mitigation system is the pressure from the soil below the slab to inside the building. That pressure differential is the most critical metric, because if you have a negative pressure below the slab, vapors are not going to come up into the building. And the way that you do that is you put in little test points, and vapor pins make excellent test points because they stay there and they're referenceable monuments. But you want to put these test points in areas that are most distant from the suction point and at the outer extent of the negative pressure field. And there's usually some fluctuation around the outer foundation of the building. So you want to make sure that this area is also kept under pressure. And this is because foundations are leaky and the system really needs to be performing so no soil chemicals get in the building. This is easy to monitor with a micromanometer like you see on the right there, or you can find the weakest point in the pressure field and embed an electronic sensor, and the other points will simply be relational data. This here is a graph of how a vapor intrusion mitigation system is performing. And this one has no controls on it, which means the motor just runs at full speed all the time. The blue line is the sub-slab vacuum, and the red line is temperature in Fahrenheit. But you can see there's a direct relationship between temperature changes and pressure changes within buildings. And that's because that warm air inside the building is always wanting to rise, and that's what's creating your vacuum pressure. Now, the colder it is outside, the more that warm air is going to rise, and the more you're going to need to compensate for it with an effective vacuum below the slab. In the US, there's kind of a initiative underfoot to use airflow as a metric. But when we integrate dynamic controls or response-driven controls, and what that is, there's a sensor below the slab that controls the speed of the motor and the vacuum applied to the soil. This system here we set up to monitor hold the pressure differential steady at 2 pascals. And the red line represents the temperature changes, and it got very cold and kind of warm this month. So over a 67-degree Fahrenheit change in temperature, there was a 97% change in the volume of airflow, which means that airflow is highly subjective and really only has value for assessing possibly mass flux or mass removal if you're integrating a sampling program of the riser systems. So what is the frequency that you should be taking measurements for an O&M system? Usually what happens is, depending on the contamination below the slab and how the building is used, it's going to be either monthly for the first year and then quarterly thereafter, or quarterly for the first year and then annually thereafter. So if a building is being occupied by people, and it's a multifamily building, as a lot of industrial buildings are being converted over for multifamily use, it's not unusual that you will either integrate telemetric monitoring or that you will have monitoring once a month and then move to annually. The other thing is, what are you monitoring for? What are the contaminants? Now, this is on the chemical analysis side, not on the physical metric side. And typically, if you have your subslab contaminants defined, you're only going to monitor for those metrics. Frequently monitored is the indoor air or riser air, and that's the air that's coming up from the soil gas, because as the system progresses, you may actually clean up certain sections of the building, and then you can shut those gate valves and apply the vacuum pressure to the most contaminated area. So you're managing the effluent of that contaminant. The other thing is some systems require carbon filtration, so you're not exhausting soil gases in the air, and that depends on what country you're in or what municipality and what they will let you to exhaust into the air. And this is an expensive process. So the cost of this needs to be integrated into the O&M plan, and who's going to be responsible for paying it. Now, again, if you integrate dynamic controls where you're only applying the vacuum that you need to protect people, you can extend the life of these carbon vessels by approximately 3 times, which is a very, very significant savings over the life of the project, which could be 20 years. What kind of fault notification did you have? The most basic that's accepted in the US is a manual monitoring, and that's where you have a physical mechanical gauge. You have a red light, green light that's usually hooked to a diaphragm switch, and this is strictly mechanical on off, which triggers an audio alarm. Then you have a switch on it so you can shut the alarm off, and there's a label usually right next to this that tells you who to call for maintenance. And usually somebody associated with the building is going to have to walk around once a month with a clipboard just to make sure that vacuum's being applied, but it doesn't tell you anything about the most important metric, which is the vacuum below the slab. The next level of monitoring is fault notification. Now, this is where you have sensors grouped together, and that can be subslab, airflow, electrical use, whatever you want, and it reads the telemetry out. You can't go back in and change anything, but what it will do is it will create an hour-by-hour data log of everything that functions. You can merge this with a local weather station, so you'll have the effects of the weather, and that's how I created those graphs, is by merging these 2 data sets, which is done automatically with Vapor Dynamics. And you will get email alerts of faults, or you can get a text alert of fault, but it doesn't enable you to go back in and change or manage anything. And there's no electrical power savings or savings that's accrued through this type of straight, easy monitoring. The next type of monitoring is fault notification and response-driven controls. The way this works is you take sensors that drive the motor speeds or actuate valves and things like that, and they integrate a sensor-driven system for maximum protection and electrical efficiency. And the electricity that is saved and the power cost savings from this system more than offsets the cost in the monitoring system. So what it does in your long-term stewardship plan is it mitigates the expense of running this system and almost makes it free. There's the light controls, and as you can see on the screen there's all the readouts of all the sensors, and if anyone falls out of a predetermined parameter, it will turn the light red. You'll get an email, and the consultant can set the level at which they want alarms in the initial programming, and you can also change it after the system's up and running. What this does, it provides the highest level of documentation and protection and instant notification if there's a fault, along with the power savings that can help you save money and help your client better manage the site. This here is a graph of how response-driven controls actually work in the real world. And the red line, it indicates that with fluctuations in pressure in the building, which are caused by, again, temperatures, your leading cause of vapor intrusion and convective variance. The next is, depending on the geometry of the building, is wind speed and barometer, a little bit rainfall, depending on the size of the building. So when we integrate these types of controls, the motor usually runs annualized at 38% of base speed, which is a significant savings of running it at full speed to accommodate for the worst conditions that may occur during the year. When I created this graph, the red line is what you have in actuality. The black line represents if we let the motors run at full speed all year, and the blue line was a conservancy value if it only ran at 50% of speed, not a full speed. So that's for existing buildings. The nice thing is in new construction, you can integrate all the probes and all the sensors below the slab and integrate them into the control system that monitors your pressures below the slab. You can integrate methane sensors, VOC sensors to keep a total record of what's being extracted. This works out really well when when you cannot go back and take samples from the top of the slab. And that happens frequently with pharmaceutical manufacturing, big box stores, and a lot of other types of buildings where particularly there's security-based manufacturing going on for defense departments. They like this approach because once we set it up, it all runs on telemetry and nobody has to go back to the building to measure those metrics. And they get a log of what goes on every month, every year, and they have full records of protection for the system being operated. So protection is the key word. We want to protect people, and we want to make sure that after we spend all this money on the system, that it functions a long time into the future. So we find it best when we integrate electronics to monitor this performance. Mark Cram is going to talk about that a little bit more in an upcoming presentation on the effects of pressure. And we also provide protection from long-term liability. I speak many times to boards and directors for large international corporations, and they are very, very long-term liability conscious and very risk adverse because of the increase of lawsuits. So they choose to integrate this as a common standard in how they mitigate their buildings. So ultimately, again, we want to be protective of people. And it's very important that when you design your vapor intrusion mitigation system, that you integrate response-driven controls or some type of monitoring system that has a plan and assurances that the system will function correctly and that the people will be protected. And if there's a fault, there's a plan to replace things immediately. Sometimes we'll actually buy extra motors and we'll leave them on the shelf at the site, and they'll be paid for upfront so we can instantly make repairs if in fact there's ever a failure. So I just want to thank you for listening to my presentation and the time spent today. If you have any questions, there's my email, or you can tag them into the chat, and then I'll answer them if any time is left over at the end. Thank you very much.
Thank you, Tom, for this insight in this vapor intrusion monitoring and prevention. So I will leave the desk to the other chair, to Tom, to present the other speakers.
Thanks, Antonella. So yes, keep moving on because I know that we're going to be restricted to time at the end. So we want to keep as much time for Q&A as possible. Our next speaker is Laurie Chilcote. Laurie is Director of Sales and Marketing for Colvin and Associates, and also Vice President of VaporPin Enterprises. And she's also a founding member and serves on the board of the Association of Vapor Intrusion Professionals. And Laurie's going to give a presentation on a review of the evolution of vapor intrusion. So over to you, Laurie.
Thank you very much. And thank Remtech Europe for having me today, and Marco for all of the things that he's doing for this conference. So I appreciate everybody sharing their day with me to discuss the evolution of vapor intrusion. And to fully understand the evolution, you really have to understand how did we get here. So I want to talk about the history of solvents. Back in the 60s, 70s, 80s, I mean, at its peak, TCE production was 600 million pounds. That's approximately 1 million drums of TCE. And if you think about it, an environmental manager with 30 years of experience has essentially no personal knowledge of how those solvents were used in bulk. And how did we use them? We chrome plated everything in the States, as well as using them in large volumes of consumer goods. We used them in paint. In fact, dry cleaners, there were small businesses that started up, and dry cleaners used a lot of chlorinated solvents. We also used them in painting, machining, electronics. Even in the medical field, they were used to help women during childbirth. They were used to put out fires, which dispersed a lot of chlorinated solvents, also as pest controls. So how did they dispose of all those 1 million pounds? In the Chemical Data Sheets Manufacturing Chemist Association in 1968, they just said to pour it on the dry sand in the earth, bury it away from water supply. And even the ASTM standard in 62 said to pour it on the ground, and that's exactly what they did. So then they started coming out with guidance, and guidance plays a very important role in vapor intrusion. The US EPA does have some vital information that can be very useful on their website, such as the Viscal calculator, which is used worldwide. ITRC is a good for practitioners. They have great guidance regarding vapor intrusion pathways, as well as petroleum vapor intrusion guidance that's used around the world. In general, the United States has a mixed bag. Some states have guidance, some don't have any guidance at all. AVIP, the Association of Vapor Intrusion Professionals, actually provides guidance documents all in one central location, including international guidance documents. Let's talk a little bit about that ASTM standard, specifically E2600. It's used in real estate transactions to see if you have a vapor encroachment situation, but it's based entirely on the groundwater to indoor air pathway. So it's not very applicable to most sites. We actually took some of our sites that we knew had a vapor intrusion issue and went through this flow chart and found that they would have passed with flying colors. So we suggest that you take this out of your toolbox. There's many organizations all over the world that are working on establishing accepted and recognized best practices and credentialing standards for vapor intrusion professionals. So those are some organizations to keep in mind, and that's grown and changed over the years. As radon, it's been in the back pocket. It's becoming more important role in vapor intrusion in terms of possibly a predictor of when to take soil gas samples. But radon is different. They're regulated differently, primarily because radon's naturally occurring, vapor intrusion isn't, and you can't sue Mother Nature. Subslab depressurization system can possibly solve both VI and radon problems. And there's some now government loans for new multifamily dwellings in the EPA radon zone 1. And these are the dark red ones is where radon is actually being evaluated as a possible predictor of when to take soil gas samples. And we'll dig deeper into that. So let's talk about the nuts and bolts of the evolution of VI. We're going to take about concept development and where we started. First, we all talked about don't go in the early days. Back in 2000, all of the guidance was to not take a sample inside the building. Do whatever you can to not take that sample. And that has definitely changed now. Predictive modeling, the next thing that came along was, well, if you can't take a sample inside, how are we going to predict what the indoor concentrations are going to be? So Johnson and Edinger's predictive modeling was used quite a bit. And then sampling techniques. We worked on the techniques on how we were going to collect sample, what's the right kind of equipment, what kind of tubing should we use. There was a lot of work to sort out and how to collect a proper sample. And they were really taking a lot of basing them off groundwater samples, which were really not going to be what was needed in the long run. So in the start, we ended up building these little wells that were underneath the slab that was kind of nonsense that came out of groundwater. So that's where we were starting. Then there were study houses that were both on the West Coast and the Midwest, and they were informative in the early stages, but as time has evolved, we have come to see that there were some things that they didn't take into consideration, such as preferential pathways. There's a lot of data from those houses that keeps coming through the literature that you have to be a little careful about how much weight you put on the conclusion. Then standards development. So based on all the information that we have obtained to date, guidance documents were starting to be written. Every state seemed to have their own standards, and every country has their own standards as well. It's all sort of congealed upon this fiscal calculator, and a lot of people are now rewriting the standards to say, just go to the EPA standard and get that concentration from there. So then we refined our practices. That was into the next phase. And after the big concept where we started, they refined them by developing the conceptual site models. So you start the building on those conceptual site models to understand how and where we needed to take those samples. And I think in the future, we'll start using these as more decision makers, not just a way to think about the site, but actually a way to evaluate your data. And I'll show you that as we go along. High resolution sampling is just another word for lots of data. I mean, the more data you have overall will help you get a clear understanding of what's actually underneath any of your buildings. And in the past, we were doing the concept development, the sampling techniques. You'd spend so much time collecting one sample because you built that well, but now you can take 10 to 20 samples or up to 100 samples a day, or even continuous monitoring. So those are things to keep in mind. Multiple lines of evidence. It's not just taking that one sample. Now we're doing that like we did in the concept. We're using temperature, we're using pressure, you're taking soil gas samples. So you're really understanding the groundwater that's outside and what's the groundwater flow. It's very important to have that multiple line of evidence going forward. And then overcoming temporal variability. One of the things that we did learn from the study houses is that indoor air concentrations vary widely during the day. As air conditioners come on, people open windows and shut windows. These kind of things. However, the groundwater and the soil gas subslab concentrations don't tend to vary that much. So we have to do is overcome the temporal variability in the indoor air so we can figure out what's a proper sample and what does that mean. So there's advances in mitigation, more vapor barriers, liners that they're moving on with. And then what are our expectations that we see going forward? Well, sewers. I mean, definitely taking on a new, big, important multiple line of evidence role with regards to preferential pathways. And what we found is that we've looked at a lot of neighborhoods and done studies of a large number of houses in the neighborhood. And one study, we found at least half of those were affected by the sewer gas, not the subslab soil gas. So it's interesting, and I think we'll see that sewers take vapor intrusion into a much wider area than we originally thought, and I'll dig deeper into that in a case study that I have. Predictive sampling, we're going to be user pressure testing, continuous monitoring early in the project to get a feel for how the building reacts, even some radon information to help determine when is the exact time or a better time to take that VI sample. And long-term monitoring is going to become a big deal because when you put in the mitigation systems, we thought that that was the end. And actually, it's just kind of the beginning, because now we've got to mitigate. Now that we got it mitigated, we have to prove that the mitigation is still working, and we have to prove that the source has gone away so we can turn off the mitigation system. So there will be a lot of long-term monitoring and we're hoping that with this, it will be based on differential pressure instead of sampling based, but we'll see how that comes out. And that's even underneath vapor barriers. So there's also mitigation as building code in Canada, for example. They're initiating that, especially in the radon realm of things, that there is a code that you have to be able to, they're basically putting in a system of when the building's being built. And we're seeing that a lot in New York too. They're requiring resistant barriers beneath new buildings that include preset monitoring points, such as with vapor pin inserts. Okay, now let's talk about some BI technology real quick. There's a lot of varieties out there, both in sampling, PIDs, SUMA canisters, flux chambers, and vapor pins. And then even in mitigation, just try and understand what you're trying to accomplish, your goals, and obtain the results you're working to achieve so you can use the right tool for the job. So let's talk about some case studies. So this is in Illinois. It's a source of a vapor intrusion in a 60,000 square foot building. The previous consultant evaluated it for 2 years and was unable to locate the source. They knew it had to be mitigated, but they didn't know where the source was in order to start that mitigation. This is where the previous consultant had taken their samples. The yellow triangles are soil borings and the red circles are monitor wells. So keep that in mind. So we came in and installed, screened, and sampled 90 vapor pen sampling points in 2 days using a PID. We screened the site, and then samples were collected at each point per the client's request. This was PCE, this was TCE, and this was TCA. So the outcome in a week's time, and this is how we've refined and evolved in vapor intrusion, they were using groundwater samples and could not locate the source of the VI issue. Well, that's because if you're trying to locate a source for VI, you really should take a soil gas sample to understand that. So just as a reminder, this is where they took their sample. It was in a receptionist area, and it used to be a machine shop. So let's dive a little bit deeper into sewer gas and how that is a preferential pathway, and how important it is to, when you're in this case study from a neighborhood, and we looked at it, and it's basically a house that we've done and to plot data on so that we can make evaluations of the data, because there's so many different types of data. So it's better to do it visually because it generally does a better job at really showing you how that is. So we had 2 ambient air samples, 1 upwind and 1 downwind. We had a soil gas sample that was exterior to the house. We had a sewer gas sample that was collected from a clean out, but we placed it down in the sewers to help us visualize it a bit better. And then we had a crawl space sample, which was underneath the house. And we had 2 restroom samples, 1 on the first floor and 1 on the second floor. And then 2 living space samples. So we had 9 samples altogether at this house, which was a typical house. Every house in that neighborhood, we did the same level of effort, and we did it 2 or 3 times a year. So it's very intensive sampling. So let's take a look at the data. So we plotted the ratio of the compounds of concern so we could get a visual idea of the relative concentrations. What you see is in the indoor air, it looks exactly the same, and it doesn't really look like the crawl space sample. So we don't think it's a source. If we just, to start off at this level, the sewer gas seems to be really, really heavy in PCE, which is blue. So we don't think that's really the source. However, the soil gas looks like a little bit reminiscent of what's in the indoor air or the indoor. So we may be the source. Let's take another look at that compound. We added THF, tetrahydrofuran. It's found in a lot of sewer gas, and we recommend that you include and add these preferential pathway compounds onto your conceptual site model. As shown here, the relative concentrations of THF and sewer gas are pretty big, and they're also showing up in the restroom sample. That's a key indicator that there could be an element of sewer gas affecting this house. But we also noticed that it's not seen in the indoor air. So we're kind of curious about why is that? Keep in mind that THF has a half-life of approximately 30 minutes and starts to degrade naturally. And by the time it gets to the living space, it's probably degraded below the detection limit, below the detection limit, which may be why we're not seeing it in the living space on the right, which is over here. We also wanted to verify if there was an indoor air source. So we looked at tetrachlorofluoromethane, you can say that slowly, which is a common compound that we saw throughout the neighborhoods. And where we look at the data, we see that it's only found in the house. So there's an indoor air source. And by plotting data visually on your conceptual site model, it paints a clear picture of where sources are and who may be the suspect of those vapor intrusion issues. What we concluded were there were 2 sources. Sewer gas was a contributor, and so was the crawl space. The indoor air that we see in the living space does have TCE in it, which is the red compound. It does have PCE in it, which is the blue compound. So the PCE and the THF is coming from the sewer gas, and the crawl space is contributing TCE and TCA, which is light blue. The plumber came in and fixed out the plumbing and then we took out some containers out of the crawl space, and the house was mitigated. So with that, I want to thank you very much for your time and for your attention. And I'll answer questions in the panel.
Thanks very much, Lauriane, for keeping well to time there. So we're going to move to our next speaker, who is Mark Pram. And I believe, Mark, you're actually doing the next 2 presentations. So Mark is a hydrogeochemist with more than 30 years experience. He's the founder and CTO of Groundswell Technology, a group specializing in automated cloud-based monitoring and modeling of environmental sensor and analytical instrumentation networks. And he's going to give his first presentation on overcoming shortcomings of traditional vapor intrusion sampling approaches via continuous automated monitoring and response. So, hand over to you, Mark.
Thank you very much. Can you hear me okay?
Yeah.
Wonderful. It's pretty early for me, but I'm going to try to go as fast as possible, make up a little time here. It's an honor to be here, and the presentation so far, I've learned so much, so thank you. I'd like to give a shout out to my colleagues. One of my colleagues, Tom, is actually at the event right now, so go and check him out if you can. I'm going to cover some things that I love how Lori framed this. I think it's perfect being right after what she stated. A lot of folks early on, and even to this day, they believe that there's this static situation. If you look at this chart here, you see concentration. It doesn't even matter what the value is, but over several days. And the reason they think that is because of the sampling method used. So here we see a Suma canister. And if you look, you'll see that there's one result there that's supposed to represent a time-weighted average. And I've seen canisters and sorbent systems out there for anywhere from 10 minutes to 30 days. And they get a reading, and then they try to come up with an explanation for the result. Here's what actually we often see when we're using continuous monitoring. And you can see that there are some factors that control the dynamics. And I submit to you that if you understand those factors, then you can best understand not only how to address it, but when to sample and how to derive the most effective assessment of whether or not there's a risk. The dynamics are obviously caused by many different factors. This came from California guidance that I think is pretty good, but you can see that you've got outdoor air, you've got sewer, you've got indoor, you've got soil vapor. And I saw that Frank was asking about advection. I believe that in the shallow subsurface, advection dominates, and I have data to support that. And so there's so many different variables, groundwater, soil, etc. And the earth is breathing in and out continuously. And we'll show you a little bit about this. Whenever we're asked to go out and make an assessment, I ask the people, what is the objective? What are the key questions you're trying to answer? So typically you want to know, is there an exceedance? And if there's an exceedance, is it because of indoor source or is it because of vapor intrusion? If there's an indoor source, where is that and what is it? If it's really vapor intrusion, where are the vapor entry points and how long is it occurring for? And then what can be done to immediately reduce that risk? And then follow on, how effective did you address that? And again, I submit to you, and as you saw from Tom and Lori, dynamic data patterns can give you these answers. So if you're using passive canister and sorbent samples, I think they have a role to play, and they're very useful for a lot of screening types of approaches. But you just get that one number over the sampling period. So you can't see this pattern and you can't answer some of those questions, at least not immediately. And there's no real-time feedback. Therefore, if you're thinking about if you accept that what a lot of regulators are accepting, that trichloroethylene represents an acute risk, or maybe even methane is an explosion risk, by the time you collect the sample and get the result from the lab, you've already exceeded the duration of concern. And we see false negatives and positives all the time. And there's something called reasonable maximum exposure that I'll talk about in the next talk that you can't really address as well if it's randomly timed type of sample. And it becomes costly if you have to go out for multiple events, which is often guaranteed. But with continuous analyzers, you can determine the duration of exposure. You can see the spatial and temporal pattern. You can understand what happens when you're inducing some changes like pressure changes or turning on ventilation systems. And you can not only immediately respond, but you can automate a response. So, you know, getting back to what Tom was focusing on, which is, you know, what are we really trying to do? We're trying to protect the occupants and also prevent liability. And oftentimes when you have the right data in a single mobilization, you can respond, answer these questions. The system that we're using is a customized gas chromatograph. We've made some modifications. I don't want to get into too many details because of time, but basically we made it so that with a single instrument, we can monitor from multiple locations. So we have a series of pumps that pull samples in, and then we control it like a robot. We send the data to the internet, and then we can also reach into it and change the operational parameters remotely. The data is not a screening tool. It's not a handheld PID. It's analyte specific. It's quantitative. It's actually an EPA method, TO14A modified method. Very stable, very fast, less than 10-minute analytical time. I mentioned you can control this remotely, and all the data is through the cloud. But what also is very powerful is you can switch from monitoring mode to discrete sample mode. So if something arises, like all of a sudden you see you know, a detection that you didn't expect, you can run out really quickly and analyze that while the instrument's still there. A couple pictures. There's a gentleman that is deploying some of the nylon tubing. Obviously this is in a dry cleaner. Here's a couple of shots here at different deployments. You can see it's about the size of a microwave machine. So a little card table is all you need. We need to have a gas cylinder and a computer, and sometimes additional telemetry units. This is a situation where we rented an RV and I converted it to a mobile lab, and we rapidly screened an entire neighborhood. And then for those homes where we thought we'd need more information because we got a detection, we wanted to see the range of concentration, we then parked it in the driveway and then monitored for a day or a couple of days. So the data we get is concentration, differential pressure, weather conditions, and then we present this in a pretty intuitive dashboard. It doesn't take much training to become comfortable, but you look at the data, time series, stacked time series, spatial renderings, moving averages, alerts. You can trigger relays. You could even engage a sampler at the right time. So you can automate that. It's all web-based, and you can click on a box and get daily reports. I'm not going to go into too many details, but here you can see spatial as well as temporal, and you also have an alert component at the bottom where if you set a threshold for a specific location or multiple locations, if you've exceeded that threshold, it'll track that. So I'll go through a couple of quick examples, and all of these examples are where previous sampling events occurred. Sorbents or canisters or both had already been deployed and data was collected already, and they still couldn't answer those questions. And I had to dig deep because we've been out to close to 200 sites now. So I just picked a few to make a few, you know, relay a few lessons here. But as I mentioned, you couldn't answer critical questions. Is it an indoor source or is it vapor intrusion? What's the controlling factor? Is the mitigation system working? And for each of these examples, a couple of days of monitoring was all that was required, and we were able to get the project to the next level. Here's one some folks may have seen me talk about before. It was a federal facility, a very large, over 100,000 square foot facility, and they had been evaluating this for over 7 years using traditional approaches, and they kept on getting hits every couple of quarters or so, but they weren't sure why. This is for TCE. So as Dr. Hartman was walking around in discrete mode, he came across a room that had a drain, and he took a sample in the drain, and we got a little bit of a detection, and it was getting close to quitting time. So he said, you know what, I'm going to put it in monitoring mode overnight because I'm just going to go back to my hotel and have dinner and then sleep and come back the next day. And so as you can see, at about 5 o'clock when the door closed, you can see a steady rise. I submit to you that the slope of that curve is related to the flux, okay? And then as soon as the door was open the next morning, we saw it drop, and then we closed the door again, you saw it rise. So that was very quick, and we were able to identify that pathway. That was very intuitive and simple for everybody to understand. Here is an example at a dry cleaner, a former dry cleaner, where we see this diagnostic pattern. I call it a butterfly pattern. So we've got tetrachloroethylene on the top, barometric pressure, and differential pressure. And as you can see, there's an inflection right here where the barometric pressure drops. And I believe what's happening is that the subsurface doesn't equilibrate right away. And so you have a pressure differential, you have a gradient that is focused upwards, and the earth basically exhales. And you see this in the differential pressure, where in this case, a positive differential pressure means the subsurface has a higher pressure than indoors, okay? And as the earth exhales, the soil pores have PCE, and they move through the slab into that structure. So that's a really nice diagnostic that tells you, yes, you have vapor intrusion. Basically, the barometric pressure drop, and it doesn't even have to be a lot of pressure, slight pressure drop leads to differential pressure, leads to vapor intrusion. Now here's a mitigation system. There was a very large slab. As Tom was talking about, some of these large structures can be very challenging because you might not be able to get the sufficient differential pressure to maintain control. And in this case, we're monitoring 4 different locations at the same time. And as soon as the mitigation system was engaged, it's intuitively obvious to the most casual observer that this system was working, because you got an immediate drop in the concentration down to below our detection level. Okay, this last example, hopefully I've got time here. This was a situation where it was a former furniture or a current furniture manufacturing facility, and the building was for sale, and they were getting an offer of $2 million less than asking price. And the reason was because they had previous data of canister data and a couple of subslab samples as well. So we started monitoring in the afternoon as soon as everybody left for the day, and we didn't really see much. And then as soon as everybody showed up the next day, we saw these large hits. If your eyes are good, you can see over 200 microgram per cubic meter of TCE. And then it dropped off at the end of the shift. And this was ubiquitous throughout the facility at multiple locations that we were monitoring. So we started looking around, and the consultant was very clever. He was walking around with Dr. Hartman, and they said, well, what's going on? And they were using this silicone spray on some of the machines. And so we looked at the labels. TCE was not listed, okay? So we were thinking, well, you know, what do we do? And Dr. Hartman had a great idea. He said, I have the machine here. Let's analyze some of this. And sure enough, we got a chromatograph of that system and of that material, and we saw TCE was definitely in that spray. So we removed that, and we resolved that issue. Vapor intrusion was not a big contributor to what we were seeing there. This was multiple lines of evidence, a couple days of monitoring. Traditional methods, they had been out there multiple times and kept getting, you know, curious results. But we were able to accurately source this, and within a couple of days, we were able to solve this problem, and then they got full asking price. So with 3 field days, the owner made essentially $2 million US. In summary, we've done well over 100 projects. Most have already had data. And so what if I can leave you with a parting thought is, maybe try continuous monitoring earlier on, instead of going back and repeating the same thing and getting you know, locked in a quagmire of mystery. The continuous monitoring data pattern is an opportunity to help you resolve this. You can rapidly address, more often than not, in a single mobilization, whether or not there's a risk, whether or not there's an urgent exceedance of an acute risk driver, if there's indoor sources or where the pathways might be. And it's great for effectiveness, design, and optimization of remediation and mitigation. It's great for brownfields where you're looking at redevelopment. And also you can rapidly screen large neighborhoods. The other thing is you can prevent acute exposures as well. And so I'd like to thank my colleagues for that. And I believe I'll be going into the next presentation as well. Is that correct?
Yeah, that is. Mark, thank you. Again, thanks for keeping to time. So I'll let you just change your presentation.
Okay. This one is going to be controversial. I'm just warning you all, and it's very early for me. So hopefully attitude doesn't come through in a way I didn't intend. I want to also shout out to all the folks that worked on this from various countries. We've got Australia, we've got Europe, we have Brazil, and obviously the United States. But I'm going to talk about risk evaluation using automated continuous chemical and physical parameter monitoring. So we saw this image before. There are many different things that can create a dynamic setting for exposures. And early on in this industry, almost 10 years ago, this was finally codified, but people started to think about spatial and temporal dynamics. And not only that, but now Dr. Holton, who was studying under Dr. Johnson at the time, they concluded in this groundbreaking article that there can be relatively high probabilities of false negative decisions and poor characterization of long-term mean concentrations with the sparse data typical of current practice. And at that time, they weren't using the types of things that I was just talking about, with very few exceptions. Now, if you look at the 2015 guidance, the EPA guidance, this is the quote unquote Bible. It's very difficult to get through, but I encourage you to try. If you read the details, and this is mentioned over 10 times, they talk about reasonable maximum exposure, RME. They mention it over and over and over, and they say that they recommend that all the risk-based decisions should rely upon this estimate of the reasonable maximum exposure. In our country, nobody's following that. 0 people are following that right now, okay? Now, there is a group that's with EPA and DOD, the Department of Defense is helping fund this. And they've been producing great work where they're looking at trying to improve the timing of samples, sample collection efforts, so that you can capture the reasonable maximum exposure. And they are looking at everything else as randomly timed. And in this article that I encourage you to read, Dr. Henry Shuver from EPA headquarters and some other folks from private sector that are very talented individuals, their conclusion was that you would require 58 randomly timed samples to meet the reasonable maximum exposure criteria. That's just not practical. All right. And so nobody's doing it. They're basically ignoring it. Here's a couple of quotes as well. Past research on highly variable indoor air data sets demonstrates that conventional sampling schemes can result in false negative determinations of potential risk corresponding to RME. So they're looking at controlling factors, and they're trying to encourage people to look at these: radon, differential pressure, temperature, etc. Okay, so as I mentioned, we can use high frequency continuous chemical monitoring to evaluate vapor intrusion at the proper times. And I'll get in a little bit more detail in a bit. But basically, as I mentioned earlier, you can determine the duration, you can see the patterns, and you can immediately respond. And typically you can do this in one mobilization. Now, if you couple the chemical with physical controlling factors, like what people are doing, which you'd be surprised, just by people moving through the system or turning on, opening, closing doors, we see so many things that will impact the chemical observations. HVAC systems, plus natural, like I mentioned earlier, the barometric pressure trend, not necessarily the absolute value, but the trend. and anything else that can influence the differential pressure across the slab. This is wonderful to collect all this data at the same time. Again, you've seen our system. We've been on 4 continents. We're expanding that hopefully pretty soon. Again, I've already gone through this slide, so no need to repeat. Here's one of our differential pressure systems. The one that Tom showed is really great. It's excellent for this type of application. Our system, we couldn't find one that was commercialized that were wireless, and we wanted to couple all the data live with the live chemistry. So we built our own systems, and we couple this to weather, we couple it to the chemistry as well. And so here's some data from a large Department of Defense facility down in the coastal region of Southern California, San Diego. And we're looking at, in blue, TCE concentration. And you can see that it exceeded over 400 micrograms per cubic meter on one of these days. And barometric pressure. So you see that pattern I was talking about before. A dropping trend in pressure leads to the earth exhaling, and you get the whatever's in those pores moving through into the building. And then green here is differential pressure, and you can see a beautiful temporal correlation as well. These are over 9 days. If you count these big peaks, they're like 9 peaks, right? So basically that daily barometric pressure change leads to that differential pressure, leads to vapor intrusion, and that flux direction is critical. This gets back to some of the earlier talks about, oxygen in a static environment. I maintain that I've seen where oxygen gets depleted pretty quickly when you have a dropping barometric pressure. Okay, so let's focus here on one of these time steps or one of these ranges here. I picked the highest peak, and I'm going to look at the time-weighted average variability. So more specifically, what we did was we took 3 24-hour and 3 8-hour windows of time to simulate or emulate a canister or a sorbent type of sample over those windows. And then we compared those results. And so this table's a little busy, so what I'll do is I'll focus on a few things. We're looking at duration, the time range, the time-weighted average, and the complete range. And let's pick a few out here. Here, in this case, with 5 hours difference starting time, you get a vastly different result, okay? All of these overlap that peak somewhat, but not all at the heart of that peak. So if you look at that in California where this was, the regulatory recommendation would be an accelerated versus an imminent response. So that means fix in weeks versus get out of the building right away, okay? Now, a randomly timed sample, the chances of you getting right on that spot where it's the most reasonable maximum exposure, if you will, is negligible. It's probably not going to happen. So the time-weighted average depends upon whether the sampling window coincides with upward advective flux conditions. Traditional randomly timed samples can yield various conclusions that might not be preventative, right? Continuous monitoring allows you to derive a reasonable maximum exposure during upward flux, right? And also what's really nice that falls out of this is that if you are looking at this and you are tracking conditions that suggest upward flux, but you don't measure an exceedance, then you don't need to repeat this, right? You've already said it's safe. The other thing is that we are locked in the seasonal mythology, if you will, of where we say, let's go in the summer, let's go in the winter. We're ignoring pressure. Let's go when the pressure's saying upward flux in the summer and when the pressure's saying upward flux in the winter. Please, let's do this correctly. It's not magical that it, because a lot of people go out on a nice sunny day in the wintertime where I live and you'll have a high pressure dominating, okay? Also, I think this has implications with the arguments that you're hearing about what's an appropriate attenuation factor. Every attenuation factor study that's out there was using randomly timed samples. Should reasonable maximum exposure estimates be considered in that? I throw that out for discussion. Okay, the pattern is key. We evaluated elevated values we saw in these 6 to 12-hour periods. So the sample timing is critical. The highs correlated with the differential pressure. The barometric pressure absolute value is meaningless to me. It's the trend. Is it rising or is it falling? And so we can now assess risk over the proper time windows. If there's no exceedance during upward flux conditions, it implies that there's no risk. This is analogous to building pressure cycling. However, in building pressure cycling, you're inducing a pressure gradient. And also you're limited by the size of the building and leaks and things like that. This is just using natural conditions that people might be exposed to. So I'll conclude. We saw that the time-weighted averages ranged pretty dramatically, and it was dependent upon the sample duration and the timing. It depended upon whether there was upward flux. Due to the concentration dynamics, randomly timed, time-integrated sampling approaches are going to yield different results, different risk estimates, and different response recommendations from the regulator. Continuous high-frequency monitoring of the indoor chemical concentration with these controlling factors allows you to determine a representative risk assessment. It also can produce results that I believe are more closely aligned with EPA's objective of reasonable maximum exposure. When correlations between continuous monitoring of chemical concentrations and controlling factors can be documented, this can be used to determine whether or not there's a risk. You can design campaigns for optimal sample timing. You can use trigger criteria, and you can automate that. And you can also derive site-specific attenuation factors. And then you can rapidly conclude whether to close a site or not. So I'd like to, again, give a shout out to my colleagues. Tom is there in Italy. I wish I were there drinking Brunello with you at the moment, but it didn't allow for it this time. But thank you very much. It's an honor to present to you.
And we wish you were here too, Mark.
Thanks a lot, Mark. Actually, thanks a lot to all 6 speakers. I think we had really 6 extremely interesting presentations. I learned a lot. It's also a lot of variation in the presentation. I think we had a very interesting session so far. We have ample of time. We have half an hour for discussion. And we have quite a number of questions for all of you. However, I like to open with one general question that bothers me a bit. When we started with our paper intrusion assessments, we realized you have several ways of transport of volatile pollutants. You have the advection in soil water, which probably is not very important. You have the advection in soil gas, and you have the diffusion pathway. In the beginning, we believed that the advection in soil air was dominant. Now, since we have our insulated houses, we're not in the northern part of Europe. It's not like Florida or California where we have the doors open all the time. We have clay soils in which the advection is generally limited compared to diffusion. You all seem to conclude very easily that advection is dominant over diffusion. Can you put that so easily? Can one of you respond to that question, please? One of the speakers. Isn't it possible that in some cases diffusion is the controlling mechanism?
This is Mark. I think every site is like a snowflake. And I've seen where diffusion dominated. I see that in the deeper soil in particular, but I've also seen pressure dominated migration of things like oxygen and methane as deep as 8 meters at some of the sites I've been to. But I agree with you. I think it's a combination. But when advection, when the machine is on, advection blows all the models out the door that assume only diffusive flux.
This is Tom Hatton. I would agree with Mark. Every site is absolutely different. Every site has its own fingerprint. And that's largely contingent upon the permeability of the soil beneath the slab and the spaces that are between the soil pores and the integrity of the slab. You take those two factors and then combine them with your changes in weather, temperature, barometer, and what the geometry of the building is also critical as an air mass moves around it. And the temperature of that air mass that flows around the building is going to create a different vacuum on the building. The colder the air is, the more dynamic that transfer of pressure is going to be. So that's why taking this approach like Mark just described and things that Lori talked about is very important in assigning a fingerprint that's based on those factors to each building. The way I got into this business was EPA thought that diffusion was the biggest model. And in '85, I proposed another model that was based on the factors that Mark and I covered in our talk.
And this is Lori.
What about the input? Sorry, yeah, Lori, please go ahead. You first. Yes, please.
Well, I was just going to mention that, we're talking about diffusion of soil and into the building, but sometimes you have the preferential pathways that bring the contamination into the buildings. And there could, especially from industrial sites that are pouring things down the drain because they have a way and allowed to do that. And then the sewers lines break and it gets into the soil, or it just comes up into the house, or people bring it into the house. So those are things to consider as well.
I have a comment, but it's maybe typical of Italy, because in Italy we are not usual to construct buildings on clay or fine soils because we have many seismic problems and other things that can affect the building construction. So in many cases we have below the building not the natural soil, but soil that is used for the foundation of the building, and it has a different characteristics with respect to natural soil, and this layer can affect the advective part of the vapor intrusion below the building. I don't know if in other countries there is the same problems, but in Italy is typical of all the buildings.
Okay. Well, I'm pretty convinced of your explanations of the role of advection. I only have one further detailed question. What is the impact of climate on the role of diffusion versus advection? It's different in a tropical region than in a temperate region, I believe. Is that true?
Yes, that's something
Go ahead, Tom.
I talked about. Yeah, I talked about that 2 days ago in an earlier presentation. The more variable the climate, the more variable the pressure changes within the building. And I would agree with Lori that slab integrity is very critical. And another thing is the oldest civil engineering drawings that I've ever seen were from Rome about 2,000 years ago. And they actually had round stones in the drawing below the slab, which showed me that you're the most advanced thinkers about sub-slab permeability. So yes.
Anybody else want to comment?
I have a theory. I think that we're seeing dramatic swings in climate in certain areas. We certainly are in California where I live. And so let's think about the implications on vapor intrusion. If it would create a larger differential pressure, would that induce more vapor intrusion?
That sounds convincing.
So
Yes.
it depends on the, for example, on the differences in temperature between soil and air, or is only a pressure matter? Because the temperature variation in soil, even in Rome, when I live, where the temperature are always high, is not so variable, but the temperature in the building can vary across the day and across the seasons.
Okay, shall we skip to the chats, or Antonella or Tom, do you have a general question, or shall we skip?
Yeah,
to
I have a general question, because vapor intrusion is managed, I think, in different way from Europe and the US, because I think Frank can correct me if I'm wrong. In Europe, we use the assessment of the risks for vapor intrusion to give quality objectives to soil and groundwater. We are more focused on the source and less focused on the receptor. I think in the US, you are more focused on receptors and on the exposure and risks, and less focused on the source. And that's why I asked who will pay for this investigation and mitigation of vapor intrusion. Because in Italy, if somebody contaminate soil, is responsible for all the risks that contamination can cause to buildings, to people, and so on, and to the environment. So it's not possible in Italy to push the owner of the house to pay for monitoring and for mitigate the vapor intrusion. I don't know if in the Netherlands is the same situation. So we look more to the source, to the intervention on the source, than to the intervention on the receptor, because the source is for the source is liable the polluter. The receptor can pay for its safe. So this is
that's indeed similar in the Netherlands, Antonella. Maybe anybody of the speakers like to respond to the situation in the States, for example?
Yeah, you know, Antonella, this is Lori. When we're evaluating sites, there's a lot of times that, and I do that, talked about this, about when did it happen? Because a lot of times it's the same here. Whoever was the source of the contamination is responsible for it. Sometimes even if they don't own the building, if you can trace it back, sometimes there's insurance on that building that would help pay to fix those issues and to remediate those sites. But if it is sold, if the building is sold and the buyer takes on that responsibility, it transfers to them when they make the purchase of the building. So that's what I mean by the owner who owns that spot. If they've taken on the liability, they then become responsible for taking care of the source.
I have a further general question. I asked yesterday at a training course about vapor intrusion, and the reply surprised me a little bit. You mentioned several of your speeches the role of sewers, probably very important. What about all the other utilities in the soil? The soil is saturated with cables and all kind of. We all only look at the sewers. Is that reasonable? Shouldn't we also look at all the other preferential pathways for utilities?
This is Tom. Electrical conduits are a major source of vapor intrusion because the electrical joints in the conduits are not sealed, so they don't collect water. And you can do a tracer gas study where you inject something like helium below the slab and then take the helium over to the electric panel or the outlet box, and the helium will be coming up through that. Or even if you drill a hole in a block wall, you'll pick up the helium. So there's a lot of the entry points are a lot more complex than they may look just on the surface. And that's why it's important to do this monitoring.
Yeah, we talk about homogeneous soils, but in urban areas, the soil might be homogeneous, that is all sand, but it is completely saturated with all kinds of cables. So what does the word homogeneous soil mean in this perspective?
Yeah, Frank, I fully agree with you because we in urban settings, but also in industrial settings, we found that the gases moves very far from the source because there are these many things inside the soil that can be preferential pathways for the gas to move very far from the source, and it is quite hard to identify in many cases which source can contribute to the exposure, and who is responsible for that exposure, coming back from the question I made before. And this is a very challenging issue. We tried in our guidelines, we tried to put some insight in this, to make a focus on that, and to say that also preferential pathways and all these things inside the soil should be considered for monitoring the vapor intrusion.
Yeah. Good point, Antonella. Yeah. The thing that I have against your and my suggestions here is that the vapor intrusions models generally overestimate, while they generally do not include the preferential pathway. So that's very strange to me. That's maybe a nice issue for an...
if I may, you know, I've offered this to our industry. If it's located in Southern California where I live, we'll do it at no charge. But if I have to travel somewhere, somebody can cover my travel expenses, or maybe we can get Tom, who's in Belgium, to do this. I think what needs to be done to just settle the default attenuation factor about predicting what indoor concentrations might be relative to the soil vapor concentration. Let's monitor continuously the subsurface and indoors over time, over various barometric pressure changes and differential pressure changes, temperature changes, and let's see what the ratios look like. Because the models that I've seen don't account for a lot of these things we're talking about, right? Let's go to a couple of sites, some that might be influenced by preferential pathways, some that might not, and then let's derive some empirical evidence.
Yeah, good point. Yeah, our models do account for preferential pressure differences, not for preferential pathways, but for pressure differences. That's in the models, our models at least.
If I can say regarding the preferential pathways, there are some recent works of McHugh and Beckley that estimated the attenuation factors expected using considering a preferential pathway, and the numbers that they have obtained are surely high numbers, but are in any cases lower than the ones obtained using, for instance, the Johnson and Ittinger model. This is just to say that we are not still sure about which is the real attenuation factors that we can expect in the presence of a preferential pathway. Surely preferential, when we have preferential pathway, we don't have the attenuation in the soil, but at least to my knowledge, it's still something that should be addressed.
I agree. So they came up with 0.02 and 0.025, but again, those samples indoors were randomly timed.
Yeah.
If we can watch continuously, let's try to figure out what condition might be conducive to an appropriate, reasonable estimate.
Yes, but we need screening models to assess if vapor intrusion is a potential pathway.
Sure.
And then we need a good monitoring to assess if it is a real pathway. So we need something to say vapor intrusion could be a critical pathway. So I should monitor the vapor intrusion, or it's not critical pathway. So no monitoring is needed. We need that because every time we have a volatile substance in soil or groundwater, we should make a detailed vapor intrusion monitoring, and it is not possible. It's not feasible. I think in Italy it's not feasible. I think.
Yeah.
A couple of bottles of Brunello and I'll be there.
This is, Tom, one thing I think we should look at is the aviation world has globally what they call standard atmospheric pressure, which is a combination of temperature and pressure, and it's for the globe. But each site really has its own standard atmospheric pressure, and there's going to be deviations from that. So each site would need its own fingerprint, and then we can start looking at those variations, and that could produce a site-specific attenuation model that would be more applicable than the blankets that are being suggested in the States, and maybe here too.
Okay, guys, I look at my co-chairs. Is it okay to go to some questions on the chat now? Or Tom, do you have a general question you really want to raise here?
Not a general question. I think, yeah, go to the chat, Frank, and
yes, okay,
happy to chip in later on. Thanks.
Yeah, that's good to honor the people that raise questions on the chat. A question to Marion. Is he still there? He disappeared. Yeah, you're there. Of course, yeah. Yeah. There is a question to you, Marion.
Yeah.
You already answered the questions on the mail, but I think it's nice to also discuss them in the panel. Antonello is asking, can you use sands around the chamber to get a better sealing in case of grass or stones? Can you answer that question?
My colleague Olivia Taylor will help me to answer because my English is not very, very good.
Okay, I will answer that one. Yes, we are really working on trying to have a well-sealed chamber. We have tried a lot of things. Now in quite flat area, we can have good results, as Marion showed, but we still have problems with the pebbles, and we are trying things with putting a mixture of clay and sand. But still, it's not fully convincing, because a very small leakage will lead to lower estimation of the fluxes.
Okay, thanks, Oliver. Now it's getting interesting. I had the opinion that the flux chamber measured the combined result of advection and diffusion. But Marion, you said in the chat that it is only diffusion what you measure.
Yes, because we have the chamber is closed. In fact,
yeah,
it's closed. So the pressure at the top of in the air of the chamber is in fact rapidly the same as the one it was. It keeps the same as the one at the beginning. To say the same as the air. There might be some differences. I agree. If we have pressure, if we have temperature differences, sometimes it happens. If the chamber itself is really hot, then you might have small differences. But in general, if we make it carefully, we have the same temperature of the air inside the chamber and the air outside. So the pressure shall not be different from the outside, first. And second, there's no way for the air to go out or to enter the chamber. So you will not have advective fluxes.
Okay, clear answer. Then there is a question from Mark Crum. Are you tracking barometric pressure or accounting for differential pressure of a flux gradient direction?
So in fact, that's a little bit the same that the previous one.
Yeah.
We cannot really measure advective fluxes.
Yeah.
So it doesn't mean that they don't exist. And I agree with the previous comments that have been done. In some situations, barometric pressure can have an effect, but it's a little bit specific conditions. We made a paper of that 10 years ago, I think.
Yeah.
But for the, that's for the barometric. And well, the question of the pressure difference for case where then later you will put a building on the soil, it's fully different. And I agree with all the comments that have been done previously in that the building will create this pressure difference. So then, but we cannot measure it directly with the flux chamber.
Okay.
But the idea, our idea is then to use the parameters of the chamber and all that sort of things to be able to provide some information about potential advective flux in case of a building.
Thanks very much, Olivier, and also Marian. Let's skip to Jason. There is a question, Jason, we already talked about a little bit at the beginning of the discussion. From Antonella. The question is, what do you think about infrastructures below the building and the heterogeneity of the soil between source and building, and in particularly related to the effect on biodegradation? Can you expand a little bit on that, Jason?
Yes, so preferential pathways surely play a role. We know that this play a role, we have a large evidence, but we have a large evidence regarding chlorinated solvents. In the case of petroleum vapors, I think that we should still understand what happens, because the preferential pathway is a preferential pathway for petroleum vapors, but also can be a preferential pathway for oxygen replenishment. So I think that surely preferential pathway can affect biodegradation and can affect the aerobic condition, but I don't know exactly how. And in the same way, the presence of a clay lens or an heterogeneity, the clay can can limit the oxygen penetration, but can limit also the petroleum vapors migration. So I think that is an issue not so clear. I mean, I'm not sure what can be occurred. Not so easy.
And thank you very much. And maybe the question of Mark again, he wants to know from you, can you model account for O2 depletion during barometric pumping?
Surely this can be an aspect to be addressed. In our model, in my model, I consider just diffusion, but diffusion for oxygen, while I have considered the advective components for petroleum vapors, I have not considered the fluctuation of oxygen in the first meters. So this surely can be an aspect to be addressed.
Okay, given the time, we do not have too many minutes more. I'd like to skip to Tom. Tom, you mentioned something that triggered me about new structures. You give me the opinion that you want to build in sensors in new constructions to be at the safe side and to control risk for vapor intrusion. Yeah.
Yes. What we do is
when do you do that? What type of buildings do you do that?
In pretty much all different types of buildings that are being constructed right now, what we do is we put the probe ends in the tubing into the sub slab, and then we bring it up into a common panel where you can measure pressure differential, and you can also get your samples from that panel just by doing purge volumes So if some place is manufacturing pharmaceuticals or sensitive electronics or anything where you don't want to be opening up the slab, you can just go to the panel, you can get your samples, or you can hook all those, the tubing up to pressure differentials monitors, and you can monitor the whole thing remotely, and you never have to go back into that building. And companies that manufacture sensitive aerospace components and things like that, where there's a what they call a code red area for security, they like this because nobody ever has to go back in there again. Everything can be acquired by just going to one centralized panel. So we build that into the new construction.
Yeah. I see the advantage from the risk of vapor intrusion viewpoint, but it's going to cost you.
It's going to cost you more later, because when you have to send people repeatedly into a building and you have to get them vetted for security, or if they put equipment for manufacturing over the area where the sampling port is, you can't get to it. So
okay.
You can do this all. I have a building, we did this in Iowa, and I have been monitoring that building for the last 3.5 years. I've not gone back since. That's in the United States. I just look at it on my computer screen every day.
Okay, okay. Thank you, Tom. Laurie, maybe I should put this question this way. How can I get insight in all this guidances available in US, especially since there are many outdated old protocols on the internet? What can I do to get insight in all these guidelines?
Join the Association of Vapor Intrusion Professionals. We are a group of like-minded people and professionals in the industry that are helping to organize. We have a resource on our website that you can click on any state or any country, and we've summarized what those guidance documents say and what their requirements are to help alleviate those mazes that of going through those documents yourselves. We also include ones from all over the country, different countries.
Okay, and to my opinion, you skipped a little bit easy over the lines. We need multiple lines of evidence. We need to overcome the temporal variability. This is very easily said, but not easily done. Time is lacking to go into details, but maybe let's go to the multiple lines of evidence. What are the most important lines of evidence you think you need to assess?
Well, temperature, pressure, those are all things that you want to include. Temperature, pressure, soil gas samples, and you can do that. Vapor pins get inserted, and you can take all those multiple lines of evidence with one probe, and Mark's equipment, Tom's equipment, all can make those connections to do that monitoring that gives you all those multiple lines of evidence. So it's a good point, and then any of those equipments can connect to it.
Okay. Let's continue to Mark. I also look at Antonella and Tom. I have questions, but maybe you also have questions. No. Let me see. I select one of my questions. Yeah, I didn't understand the 7 years, the 7 years experiment. What was on the x-axis of the picture you showed of the 7 years experience?
That I was just commenting that that building that I use as one of the examples that we went through. They had investigated it for 7 years. They had 7 years of at least semi-annual sampling, and they weren't able to determine where TCE was coming into the structure. And so we rapidly screened it. And then when we came across a room that had a little bit of TCE and a drain, that's when we set up the equipment and then closed the door. And within a day, we were able to find that. Yeah.
Maybe we have to finish the session. So I think I have an interesting final question for you, Mark.
Okay.
Actually, the question could be raised to everybody, but I think it's interesting to ask it to you. you showed very successful experiments and projects you did. What are the problems you cannot solve regarding vapor intrusion? What are the issues? So you told about your successes. Now I like to hear what is the lack of success? What is not possible to do? I hope
that's
you don't mind.
That's a great question. That's a great question.
Yeah.
We've had a couple of situations where we probably didn't know enough about the site. We were seeing data that was consistent, but we couldn't understand why we were seeing what we were seeing. So we weren't able to answer all the questions. What we think possibly happened at this one site in particular is that there was an indoor source that was not identified, because we saw a consistent level of TCE in this one portion of the building, and we weren't seeing it anywhere else, but we weren't able to find what that was. So one of the theories was that there could be sorption along the drywall, and that it was off-gassing. And so that was going to be the next step. So I'm waiting to hear results for that.
Okay, thank you very much, Mark, for this reply. We have to end this session. It was, to my opinion, extremely interesting session. I have the idea all of you could use more time and go in more details, and I actually would like to hear the details. We don't have the time for that. We do that next year in Ferrara, hopefully. We continue the session. Thanks all 6 speakers again for this excellent presentations and also for the discussion. Thanks all, and I give the word to Marco now to finish the session and to look forward to the next sessions.
Thank you to everybody. Thank you to you, Frank, Antonella, and to Tom for sharing this interesting session. As you can see, the program of Remtech Europe is continuing. We have seen starting in 2 minutes after we close the Sustainathon, and it is this marathon of 24 hours, and then ISAS of about the state of the art of contaminated sites in Brazil. So continue following Remtech Europe. Also tomorrow there are some interesting sessions, and that are as any session in Remtech Europe is free to join. Okay, so thanks also to all the speakers. I leave the floor, Frank, to you, Antonella, and Tom for the closing.
Okay, thanks, Marco. Okay, thanks everybody again, and I think.